The universe is far more mysterious than what meets the eye. While stars, planets, galaxies, and all visible matter might seem abundant and impressive, they represent merely a tiny fraction of what exists. Approximately 95% of our universe consists of two enigmatic components: dark matter and dark energy. These invisible cosmic constituents shape the structure and destiny of our universe, yet they cannot be directly observed or easily studied. This report explores the current scientific understanding of these mysterious cosmic components, examining their properties, potential compositions, and the fascinating theories that attempt to explain them. Before diving deeper, let's clarify the cosmic inventory. According to current observational evidence, our universe consists of dark energy, approximately 68 to 72% of the universe's total energy matter content. Dark matter, about 26% of the universe. Normal baryonic matter, only about 4% of the universe, including all stars, planets, gases, and everything we can directly observe. This reveals a profound truth. The universe we can see and interact with is merely the tip of a vast cosmic iceberg. What's even more remarkable is that despite their dominance, we still don't fully understand the nature of dark matter and dark energy. The existence of these invisible components wasn't always known. Scientists initially discovered discrepancies between what our theories predicted and what observations showed, particularly regarding the movement of galaxies and the expansion rate of the universe. These anomalies eventually led to the conclusion that something unseen was influencing cosmic dynamics. What is dark matter? Dark matter is a form of matter that does not interact with the electromagnetic force, but would still have gravitational effects on ordinary matter. Unlike normal matter, dark matter doesn't emit, absorb, or reflect light, making it essentially invisible. Its existence is inferred from gravitational effects on visible matter and the cosmic microwave background. Observational evidence. The case for dark matter comes from multiple independent lines of evidence. Galaxy rotation curves. Stars at the edges of galaxies move faster than they should based on visible matter alone. Gravitational lensing. The bending of light around massive objects reveals more mass than can be accounted for by visible matter. The movement of galaxies within clusters suggests more mass than we can see. Cosmic microwave background. The pattern of temperature fluctuations in the early universe aligns with models, including dark matter. The bullet cluster. Observations of colliding galaxy clusters show separation between visible matter and gravitational effects, strongly suggesting dark matter's existence. Theoretical candidates for dark matter. Several fascinating theoretical particles could explain dark matter. Axions, ultralight cosmic particles. Axions are hypothetical elementary particles originally proposed to solve problems in quantum chromodynamics. If they exist, axions would be extremely light particles with masses potentially millions of times lighter than electrons. Despite their tiny mass, their abundance could account for all the required dark matter. Their extremely low mass gives axions a large de Broglie wavelength, a quantum mechanical property, which might help resolve some inconsistencies between observations and predictions of the standard cosmological model on small scales. Primordial black holes. Unlike black holes formed from collapsed stars, primordial black holes would have formed in the high-density environment just after the Big Bang. These ancient black holes of various sizes could potentially account for some or all dark matter. Interest in this theory increased following gravitational wave detections of intermediate mass black hole mergers, as these objects don't fit well into our models of black hole formation from either stellar collapse or galactic center processes. Weakly interacting, massive particles, WIMPs, were long considered the leading candidates for dark matter. These hypothetical particles would interact through gravity and the weak nuclear force, but not electromagnetically, making them difficult to detect. Can dark matter form structures? An intriguing question is whether dark matter can form compact objects similar to stars or planets. This is challenging because dark matter lacks two crucial properties that allow normal matter to form dense structures. 1. An efficient mechanism to lose energy during compression. 2. A diversity of interactions needed to form complex structures. Normal matter can radiate energy away as it collapses under gravity, allowing it to form dense objects. Dark matter, interacting primarily through gravity, has difficulty shedding energy during compression, making it challenging to form compact structures. Perhaps the most startling cosmological discovery of recent decades was that the universe's expansion is accelerating rather than slowing down as previously expected. This acceleration requires an explanation, and dark energy is the leading candidate. Dark energy can be conceptualized as a negative pressure that fills the universe and works against gravity, essentially pushing space outward. Using the balloon analogy, if a balloon with dots represents galaxies in an expanding universe, dark energy is like increasingly rapid inflation of that balloon, driving the dots, galaxies, apart at an accelerating rate. Leading theories of dark energy. The nature of dark energy remains one of physics' greatest mysteries, but several compelling theories have emerged. Cosmological constant. Lambda. The simplest explanation is that dark energy is a fundamental property of space itself, a cosmological constant that Einstein originally introduced and later rejected in his equations. In this model, each cubic meter of space contains the same amount of dark energy, so as the universe expands, the total dark energy increases. Vacuum energy. Quantum field theory predicts that empty space isn't truly empty, but contains fluctuating energy fields where particles continuously pop in and out of existence. This vacuum energy could potentially explain dark energy, though calculations of its strength don't match observations. Unlike the cosmological constant, which remains unchanging, quintessence is a dynamic field that varies across time and space. This theory suggests dark energy's strength might change over the universe's history, potentially explaining some observational data better than a constant energy density. The chameleon particle. The chameleon is a hypothetical scalar particle that could explain dark energy. Its fascinating property is that its effective mass varies with the surrounding energy density. In dense environments, like Earth, its effects would be limited to less than a millimeter, but in the vast emptiness of space, it could operate over thousands of parsecs. This variable property might explain why we don't detect dark energy effects in our local environment, but see them at cosmic scales. Some of the most intriguing recent theories suggest that dark matter and dark energy might not be entirely separate phenomena, but could interact with each other. One compelling model proposes that dark energy evolves over time and is connected to dark matter through a new fifth force of nature, beyond gravity, electromagnetism, and the strong and weak nuclear forces. In this scenario, dark matter and dark energy co-evolve, influencing each other's behavior. This interacting model could potentially explain a puzzling observation from 2018 regarding the 21-centimeter signal from the universe's first stars and galaxies. The detected signal was twice as strong as predicted by standard cosmology. The interaction between dark matter and dark energy might have triggered earlier star formation, resulting in the stronger signal while still aligning with other cosmological observations. Alternative theories beyond dark matter and dark energy. While dark matter and dark energy are the mainstream explanations for observed cosmological phenomena, alternative theories attempt to explain the same observations without introducing these mysterious components. Modified gravity theories. Modified Newtonian dynamics, MOND, proposes that Newton's laws of gravity need modification at galactic scales rather than invoking invisible matter. Its relativistic generalization, tensor vector scalar gravity, TVS, attempts to incorporate these modifications into a framework compatible with general relativity, 4. However, these alternatives face significant challenges in explaining all observational evidence, particularly gravitational lensing observations and the behavior of colliding galaxy clusters like the Bullet Cluster 4. As one Reddit commenter noted, "Monde has to be fine-tuned to each individual galaxy, and even then, there are things it can't explain." Dark matter and dark energy remain at the frontier of cosmological research, representing both our greatest mysteries and our most exciting opportunities for discovery. While we can observe their effects on cosmic scales, their fundamental nature continues to elude us. The quest to understand these invisible components drives innovations in observational technology, theoretical physics, and computational modeling. Future missions like the Euclid Space Telescope, the Vera C. Rubin Observatory, and advanced particle detectors may provide crucial insights into these cosmic enigmas. What makes this field particularly fascinating is how it connects the largest scales of the universe with the smallest scales of particle physics. The solution to these cosmic puzzles may require entirely new physics beyond our current understanding, potentially revolutionizing our conception of the universe and its fundamental workings. As we continue to explore these mysteries, we're reminded that what we can directly observe represents merely 4 to 5% of reality, a humbling reminder of how much we still have to discover about our vast and mysterious universe.